The Jordan Show on YouTube.
Welcome to the deep dive. You know, we always try to explore these hidden stories, and today we're actually going deep inside rocks. We're looking at a phenomenon called isomorphic substitution. Sounds a bit technical, maybe.
It can sound that way, yeah. But it's actually a really fundamental idea for understanding minerals.
Right. So our kind of mission today is to unpack this concept and really show you why these tiny, tiny atomic swaps inside minerals actually have some pretty big consequences for the whole planet.
Exactly. We're talking about these subtle changes, almost invisible, happening inside the crystal structure. And, you know, these little swaps are behind a lot of the variety we see in rocks, how they behave, even some materials we use every day. Think about it, you know, why one rock type might handle pressure differently from another. It can come down to this.
Okay, so let's introduce the main actors here. We're talking about ions, right? Charged atoms like magnesium, iron.
Aluminum, calcium,
Yeah.
those are the big ones, yeah.
And the key thing is for them to play the substitution game, they need to be, well, compatible.
Chemically compatible, exactly. That mostly boils down to a few things. They need to be roughly the same size.
Okay.
Size matters.
It does. And they need the same electrical charge. We call that valence.
Valence, right? Like how many connections it can make.
Sort of like that, yeah. How many hands it has to link up with others. And crucially, they need to kind of fit comfortably in the same spot within the crystal structure.
Okay, so if they tick those boxes, similar size, same charge, fit in the same place.
Then you get this fascinating thing called isomorphic substitution. It literally means same form. So different ions can slot into the exact same position in that mineral's crystal lattice.
Oh.
But here's the kicker. The overall structure, the basic blueprint of the mineral, its symmetry, that stays the same.
Okay, so it's a bit like maybe musical chairs at an atomic level, or like swapping out Lego bricks of the same shape but maybe different colors.
That Lego analogy is pretty good, actually.
Yeah.
You swap red for blue, same size and shape, the building looks the same overall.
Right.
And this isn't some rare thing. It's super common in what geologists call solid solution series.
Okay, like olivine, that's one, isn't it?
Perfect example. Olivine runs on a spectrum, basically, from forsterite, which is heavy on the magnesium.
Mg Euro.
Right. All the way to phthalite, which is packed with iron, fissuro. Same basic structure, just different amounts of media and fee swapping places.
And plagioclase feldspar, that's another big one.
Absolutely. Plagioclase goes from albite, that's sodium and aluminum, to anorthite, which is calcium and aluminum. Again, swapping ions within the same feldspar framework. And even broader groups like pyroxenes, amphiboles, they show huge amounts of this kind of substitution.
So when does this swapping actually happen? Is it as the rock is forming?
Primarily, yes. The main stage for this is during the initial creation of the mineral. Think about igneous rocks forming from cooling magma.
Right, molten rock solidifying.
Exactly. As it cools, crystals start to grow, and all these different ions are floating around in the melt, essentially competing for spots in the growing lattice structure.
Like a construction site where different workers grab the available jobs.
Kind of, yeah. And it also happens a lot in metamorphic environments. High heat, high pressure. Existing minerals get squeezed and cooked, they recrystallize, and again, ions might swap places as the new or reformed mineral structures develop.
Okay, so mainly during formation, igneous and metamorphic. Does it ever happen, after the mineral's already locked in place?
That's a good question. Mostly it's set during that initial crystallization, but some minor changes can occur later. Well, if a rock gets buried again and undergoes another round of metamorphism, maybe at different conditions, you might see some limited ion exchange in the existing minerals. And chemical weathering right at the Earth's surface can sometimes leach out certain ions and maybe let others sneak in, although that often involves more complex changes than just simple substitution.
So these are just random processes happening anywhere. Where are the hot spots for this, geologically speaking?
You find it in really diverse settings. Deep down, in magma chambers where molten rock cools very slowly, allowing lots of time for these substitutions as minerals crystallize out one by one.
Okay, deep crust.
Definitely. Also, think about tectonic plate boundaries. Massive forces, intense heat and pressure. Prime conditions for metamorphism and all the atomic rearranging that goes with it.
Makes sense.
But it's not just high P, high T stuff. Even in sedimentary basins, where minerals precipitate out of water, if the water is rich in certain elements, You can get isomorphic substitution happening as those crystals form.
And can we actually see the effects of this? I mean, it's happening at the atomic level.
Remarkably, yes, sometimes we can.
Yep.
Under a microscope, looking at thin slices of rock, thin sections, geologists can spot subtle clues. Variations in how light passes through the mineral, its optical properties.
Wow, like its refractive index.
Exactly, things like that. Or even slight shifts in color can indicate that there's been some chemical substitution going on under the hood, so to speak.
Okay, right. So we've got the what, the when, the where. But the big question, I guess, is why? Why should you, listening now, care about these tiny atomic swaps? What's the real impact? The aha moment.
This is where it gets really interesting, I think, because this substitution
Yeah.
is a huge reason why minerals that are technically the same can have really different properties.
Okay, like how?
Well, take color. Ever wonder why some garnets are deep red and others are bright green?
Yeah.
Often that's down to tiny amounts of different ions substituting into the garnet structure. Same goes for density, how heavy a rock feels. Or even how easily a mineral reacts chemically, like how resistant it is to weathering.
So a bit of iron swapping in for magnesium or manganese or whatever can change its color or how tough it is.
Precisely. A small change in who's living in those atomic apartments can significantly alter things like hardness, which matters for industrial uses, like, say, abrasives.
That makes total sense. So it's not like a strict chemical formula for every mineral, but more like a range of possibilities depending on what elements were around when it formed.
You've got it. And that variability is actually an incredibly powerful tool for geologists,
How so?
because the specific ions that substitute and how much of them get in often directly reflects the conditions when the mineral formed, the temperature, the pressure, what elements were available in the magma or fluid.
Ah, so you can work backward.
Exactly. We call it geochemical fingerprinting. By analyzing the detailed chemical makeup of a mineral, including these substitutions, we can deduce a lot about the environment where that rock came from. It's like reading a tiny chemical diary left behind from millions, even billions of years ago.
Wow, so these little swaps are like clues to Earth's ancient history. That's pretty cool. Are there more practical uses today beyond understanding the past?
Oh, absolutely. This isn't just for geologists. The principles are used in material science all the time.
Really? Like what?
Making advanced ceramics, for instance. By carefully controlling which ions substitute into a ceramic's crystal structure, engineers can tweak its properties, make it stronger, more heat resistant, change its electrical conductivity.
So like for spacecraft parts or something?
Potentially, yeah. Or think about catalysts, the things used to speed up chemical reactions in industry. Sometimes adding specific substituted ions into a material can make it a much, much better catalyst.
Okay.
Even the colors and pigments, those really stable, vibrant colors in paints or even electronics, sometimes those are created by intentionally engineering isomorphic substitutions in mineral-like structures.
That's amazing. So understanding this stuff actually helps us build better materials and technologies. You also mentioned soil. How does it connect there?
Yes, soil chemistry, that's another critical area. Clay minerals, tiny, tiny minerals that are super important in soils, they exhibit a lot of isomorphic substitution.
Okay.
And often this involves swapping ions with different charges, say aluminum 3+ swaps for silicon 4+. This creates a net negative charge on the surface of the clay particle.
Ah, and that matters because...
Because that negative charge acts like a magnet for positively charged nutrient ions in the soil water, things like potassium, calcium, magnesium, ammonium. Stuff plants need to grow.
So the clays hold on to the nutrients.
Exactly. Nutrient retention. It's fundamental for soil fertility. Plus, the type and amount of substitution affects how well the soil can resist changes in pH, its buffering capacity. So yeah, these atomic details directly impact our ability to grow food.
Incredible. Okay, let's maybe get a bit more specific. Can we walk through one clear example just to see the mechanics? You mentioned olivine before.
Sure, olivine's a great one. As we said, it's a solid solution between magnesium-rich forsterite, MgO, and iron-rich phaolite, FeSiO. Now, inside the olivine crystal structure, both the iron ion, Pho, and the magnesium ion, MgO, are very similar in size, and crucially, they both have that same +2 charge.
Okay, same size, same charge. Compatibility keys.
Exactly. So they can easily swap places for each other in certain spots within the lattice. These spots are called octahedral sites, basically. The ion sits surrounded by 6 oxygen atoms.
So if the original magma was, say, really rich in magnesium?
Then, as the olivine crystals started to grow, more M-gamma ions would snap into those octahedral sites compared to Phi ions. The resulting mineral would be closer to the forsterite end of the spectrum.
And if the magma had lots of iron?
Then the opposite happens. More Fe ions win the competition for those sites, and the olivine ends up being closer to phaolite.
And this Mg-Fe ratio, it affects the properties we can actually measure.
Definitely. Phaolite, the iron-rich one, is denser, heavier for its size. It also melts at a lower temperature than forsterite, and often you can even see a color difference. Forsterite tends to be more, well, olive green, while phaolite can lean towards brownish.
And this is the really key bit, isn't it? Even with all this swapping, different amounts of iron and magnesium, the fundamental crystal structure is still olivine?
That is the absolute core concept.
Yes.
The underlying framework, how the silicon and oxygen atoms are linked together, that doesn't change. It's still the same basic olivine architecture. It's just the tenants, the MgU or Fe ions living in those specific octahedral rooms
Right.
that vary.
The structure holds even if the occupants change.
That's the essence of isomorphic same-form substitution.
Oh.
Preserving the structure despite the chemical variations.
Okay, so let's try and tie this all together for everyone listening. When you pick up a rock, even one that looks completely solid, unchanging, there's actually this hidden history inside, a whole record of these atomic level swaps and decisions that happened when its minerals first formed.
That's a great way to put it. Every crystal in that rock basically made countless tiny choices based on what ions were available in its environment,
Yeah.
what the temperature and pressure were like, choosing the best fit for its structure at that moment.
And these seemingly insignificant atomic details, this isomorphic substitution, it really explains so much of the variety we see in minerals, and it gives us these powerful clues about Earth's history and processes.
Exactly right. It lets us, read the rock story, figure out where it came from, what conditions it experienced, just by looking very closely at its chemistry.
So maybe the next time you encounter a rock, just pause for a second, appreciate that this seemingly static thing holds this incredibly dynamic history written at the atomic level. These hidden substitutions really do shape so much of our planet.
It really makes you think, doesn't it? Which leads to a final thought for you to ponder. If these tiny, subtle atomic exchanges can have such massive effects on something as solid as rock, what other parts of our world, things that seem stable or fixed, might actually be shaped by equally dynamic, maybe unseen processes happening at incredibly small scales?
A fascinating question to leave us with. It's an invitation, really, to look a bit deeper.